Let's jump right in. In this explainer, we're dissecting a seriously fascinating piece of neuroscience research about how our brains literally sync up with the outside world. Seriously, have you ever stopped to think about what's actually firing off in your head when you stare at a highly repetitive visual pattern? Well, we're going to unpack exactly that. We've got some incredible data to look at, showing the unseen ways our environment can, essentially, hijack our neural rhythms.
Just think about a strobe light, or even just a rapidly blinking screen. Imagine that flashing light as a visual metronome. We're going to explore how your brain's electrical signals actively try to lock on to that external rhythm. It's kind of like watching someone automatically start tapping their foot to catch the beat of a song playing in the background.
Okay, so let's quickly touch on the foundational concept here, the actual physiological response grounding all of this. We're talking about SSVEP, or steady-state visual evoked potentials. Now, you probably already know that when you look at a flickering light, it triggers frequency-locked neural responses right in the visual processing centers at the back of your brain. So we aren't talking about abstract thoughts. We're talking about hardwired, real-time electrical reactions to that flashing light.
Here's the roadmap for this explainer. First, syncing to flashing lights. Second, the NeuroByte framework. Third, the detection pipeline. Fourth, strong versus weak entrainment. And finally, why all of this actually matters.
All right, part 1, syncing to flashing lights, the rhythmic brain.
Let's look at the initial physical phenomenon before we get into the measurement side of things. Think of this as a literal metronome for your mind. When presented with that flashing light, your brain doesn't just passively watch it, right? It actively tries to match its internal electrical rhythms to that exact external frequency. So rather than a spontaneous thought popping up, this is externally controlled synchronization. We are literally watching the brain actively try to follow a beat dictated entirely by its environment.
Moving on to part 2, the NeuroByte framework, the toolkit used to measure the sync.
To properly measure this biological metronome effect, researchers obviously need some highly specific tools. Enter the Mumman SSVEP database, which captures just a massive amount of electrical data from subjects staring at specific flickering frequencies. They're using high-density 256-channel EEG recordings. So we're not just talking about a handful of sensors here. It's a dense, intricate net of electrodes covering the scalp, constantly pulling in a massive array of electrical activity while the subjects watch that targeted visual stimulation.
Now, with 256 channels firing constantly, there's a ton of background noise echoing across the brain. The trick is knowing exactly where to look. Since these visual responses primarily hit the back of the head, researchers zero in on specific occipital and parieto-occipital electrodes, specifically O1, OZ, O2, POZ, PO3, and PO4. By strictly focusing on this localized region of interest, they isolate the actual visual processing and entrainment, totally cutting out all that unrelated brain chatter like motor movements or just wandering thoughts.
Which brings us to part 3, the detection pipeline, the journey of a signal. So we have all this localized data, right? But how do we actually read it? Well, we start with the raw EEG and run it through a bandpass filter between 1 and 30 Hz. We do this to slice out the high-frequency static and isolate those real physiologically relevant brainwaves we actually care about. Then, after grabbing our visual region of interest, we apply a Hilbert transform. You can think of this as a clever mathematical tool that strips away all those messy squiggles to find the true underlying energy or the envelope of the signal. Finally, we normalize the whole thing using z-scores, which basically just puts all the data on a level playing field. It's a super precise funnel designed to prep the signal perfectly for analysis.
But here's the golden question. How do we decide what counts as a true brain event? It all comes down to this specific threshold number, 1.8. A candidate NeuroByte event is only officially flagged if that normalized envelope exceeds exactly 1.8 standard deviations above the baseline. Oh, and it also has to last between 30 and 500 milliseconds. That timing constraint is absolutely crucial. It makes sure researchers are catching significant, sustained neural reactions and tossing out random, fleeting electrical static.
Okay, so once those official events are detected, what are we measuring? Well, traditional analysis usually just looks at raw spectral power, but the NeuroByte framework goes deeper, extracting highly specific temporal metrics to really understand the brain's integration dynamics. We're looking at density, the literal duration of the events in milliseconds, the inter-event interval, which just means the precise gaps of time between events and how much those gaps vary, and finally, a stability index to gauge the overall rhythm. It really gives us a complete, dynamic profile of the brain's rhythmic behavior.
All right, part 4, strong versus weak entrainment, comparing the results. Now, things get really cool when we compare these temporometrics across different visual stimulation frequencies.
We can literally see what successful versus unsuccessful syncing looks like in the data. And this brilliantly backs up the core hypothesis. A brain that successfully locks onto the flicker produces highly regular, dense integration events. You see increased density, way tighter intervals between events, and much greater stability. On the flip side, a struggling brain, one with weaker entrainment, shows these erratic, spaced-out signals, reduced density, longer intervals, increased variability. It's literally the difference between a perfectly synchronized orchestra and a band that's completely lost its rhythm.
And this fits flawlessly into the ECPJ interpretation framework. It's a literal chain reaction. Visual stimulation forces neural entrainment. That flicker directly causes increased temporal coordination in the brain, meaning the density of neurobytes we measure is a direct, quantifiable scorecard of the brain's capacity to generate stable events while being externally driven. Pretty wild, right?
Finally, part 5, why this matters, the big picture.
Let's zoom out from the data pipeline for a second and talk about why measuring this visual entrainment is such a game changer. The significance here for the tech world is massive. The MAM database proves that the NeuroByte framework can reliably track externally controlled synchronization. And by proving we can accurately measure how the brain syncs to external controls, this research paves the way for highly advanced brain-computer interfaces. We're talking about a future where our thoughts and neural rhythms can seamlessly interact with machines, creating entirely new ways for humans to plug into technology.
Which leaves us with a pretty profound thought to ponder as we wrap up this explainer. If a simple flickering light can so deeply organize our brain's electrical rhythm, how do the countless other external rhythms in our modern world shape our internal neural architecture? I hope diving into this sparked your curiosity about the invisible rhythms constantly dancing through your mind, and maybe leaves you wondering just how much of your brain's activity is truly your own.